Hello, welcome to today's lesson on the wave equation. Our plan for this lesson is as follows. First, we will begin by learning the fundamental mathematical expression used to describe the behavior of waves. Next, we will understand each variable involved in the equation. Finally, we will work through some examples of applying this equation. So far, you are familiar with the features of waves and how to classify transverse and longitudinal waves. Building on this foundation, we can now introduce the wave equation, which will advance our understanding of how waves behave. Let's get started. The wave equation is a fundamental concept used to describe the behavior of waves, whether they are sound waves, light waves, or any other type of wave. The equation is V equals F multiplied by gamma, where V represents wave speed, F represents frequency, and gamma represents wavelength. This formula helps us understand how different aspects of a wave are related. Now, let's look at each aspect of the wave equation. V stands for wave speed. This is how fast the wave travels through a medium, such as air, water, or a vacuum. It is measured in meters per second. The speed can vary depending on the medium and the type of wave. The frequency, F, refers to the number of complete cycles or oscillations that occur in 1 second. It indicates how often the wave peaks pass a given point per second. Frequency is measured in hertz. Finally, wavelength is the distance between two successive identical points on a wave, such as from one peak to the next peak or from one trough to the next trough. Wavelength is measured in meters. Let's think about what this equation means. When waves travel through a certain medium, their speed remains constant. This means that if you increase the frequency of the wavelength must decrease to keep the speed constant. For example, if you have a slinky stretched out and you shake one end faster, producing more waves per second and an increased frequency, you'll notice that the distance between the waves shortens and there is a decreased wavelength. Conversely, if you shake the slinky more slowly at a lower frequency, the distance between waves increases, lengthening the wavelength. The wave speed remains unchanged throughout. Now, let's go through some examples to see how we can apply the wave equation in practical situations. Imagine we have a sound wave traveling through air, and we know that the frequency is 440 hertz and the wavelength is 0.75 meters. We want to find the speed of the sound wave in air. Using the wave equation, we can substitute the given values we have been given. This gives us a calculation of 440 hertz multiplied by 0.75 meters. When we perform the multiplication, we get a final figure of 330 meters per second. Therefore, the speed of the sound wave in this example is approximately 330 meters per second. Let's try a different problem. Imagine we have the following information regarding a wave. The frequency is 500 hertz and the speed is 1500 meters per second. We need to find the wavelength of the wave. To do this, we again start with the wave equation. Speed of the wave equals frequency of the wave multiplied by the wavelength of the wave. Next, we rearrange to solve for the wavelength. This gives us wavelength of the wave equals speed of the wave divided by frequency of the wave. We can now substitute the known values in. Wavelength of the wave equals 1500 meters per second divided by 500 hertz. WCH gives us 3 meters. Therefore, the wavelength of the wave is 3 meters. Now, let's look at a final example. Let's calculate the speed of light in water. We have the following information. Frequency of a light wave equals 4.5 times 10 to the power of 14 hertz, and wavelength of the wave in water equals 5 times 10 to the power of minus 7 meters. Again, we use the wave equation of speed equals frequency times wavelength. First, we substitute the given values, so that speed of the wave equals 4.5 times 10 to the power of 14 hertz multiplied by 5 times 10 to the power of minus 7 meters. All that's left to do now is perform the multiplication, which gives us a total of 2.25 times 10 to the power of 8 meters per second. Therefore, the speed of light in water is approximately 2.25 times 10 to the power of 8 meters per second. By working through these examples, you can see how to apply the wave equation to find any one of the variables when the other two are known. Each problem demonstrates the relationships between speed, frequency, and wavelength for different types of waves. This process will help you tackle various wave-related questions confidently. In today's lesson, we delved into the wave equation, focusing on its components and applications. The speed of the wave, v, is how fast the wave travels, measured in meters per second. The frequency of the wave, f, is the number of complete cycles per second, measured in hertz. The wavelength of the wave is the distance between consecutive identical points on the wave, measured in meters. Finally, we went through a few problems to consolidate our understanding. This lesson equipped us with the ability to use the wave equation to understand and solve problems related to wave speed, frequency, and wavelength. Watch the rest of the GCSE physics course at Sophos Education.